All right, so our mercury is currently balanced, but let's go ahead and take a look at our oxygen. So we only have one on the left, two on the right, so which side needs more oxygen, the left side or the right side, the reactants or the products? Left side reactants, right side products. Yeah, we need more on the left side, more on the reactant side. So I'm going to go ahead and add another molecule of mercury oxide, right, which is this red compound right here, very pretty, right? So let's go ahead and add another HGO here, right? And now taking a look here, now how many atoms of mercury do I have on the left? Now how many atoms of mercury do I have on the left? Yeah, I now have 2 on the left, all right, so we're going to have to fix that because now that's unbalanced. But how many oxygens do I have on the left? Again, that was my goal. How many oxygens do I have on the left now? Thank you, Christine. Thank you, Amy. More participation, please. How many oxygens do we have on the left? Thank you, Annette, Natalie, Nathan, Ryan, Ken. How many do we have on the left? Madison, hello. Yeah, we should have two on the left. Perfect. All right. So now we are balanced for our oxygens, but if we take a look, now our mercuries are unbalanced again. So we have 2 on the left, 1 on the right. Which side needs more? Do we need more on the left, the reactant side, or more on the right, the product side for mercury, the Hg atoms for mercury? Which side needs more Hgs? Yes, the right side. All right. So let's go ahead and add another Hg on the right then. So here we go. We're going to add another Hg on the right. And now I have 2 Hgs, 2 mercury atoms on the right. Oops, sorry. So the number 2. There you go. So now we're balanced. All right. So the last thing I need to do is I just need to now count up the overall molecules, the overall big circles, to figure out what are our coefficients. So over here, what should be the coefficient for mercury oxide? HGO, what should be the coefficient? Count up the number of big circles, the big molecules. Thank you. I see Christine. I see Annette. I need more participation in the chat box. How many molecules or big circles of H2O do we see on the left? Thank you. Awesome. Yeah, we should have 2. So I'm going to go ahead and put a 2 right here. That's my first coefficient. I'll go ahead and make it much bigger so that we can really see it. There we go. And how many of the HGs do we need? How many of the HGs do we need? Based on our big circles here. Yes, exactly. Same thing. We would need 2 right here. And how many O2s do we need? How many oxygens do we need on the right? Just need 1, all right, which I can actually just leave blank, right? So I can leave this blank because blank means 1. Excellent. All right, so our final balanced equation would be for every 2 molecules of red mercury oxide, this is going to decompose into 2 atoms of mercury plus 1 molecule of oxygen O2. Excellent job, everybody. All right, go ahead in the chat box, give me a rainbow if you feel comfortable with how we got this. This one is a pretty easy one to balance, so we should hopefully feel really confident about this one. There are definitely some trickier ones that we've taken a look at, but this one should be easy for us. Excellent. All right. This is minor class sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please do not share contact or social media info for your own security and legal reasons. All right, so we are taking a look today at solutions. So our objective is to be able to identify the characteristics of mixtures and solutions, which we've actually done in the past, but we are going to go more in depth about solutions. And then tomorrow that will connect back into what we've been talking about with moles. So today we don't really talk about moles very much, but we will be talking about that tomorrow. That's why we're learning about solutions today. So we should know the difference between homogeneous and heterogeneous mixtures. That's all review from Unit 1. And then we should be able to define some new stuff: solution, solute, solvent, colloid, and suspension. And here is our agenda over here on the right. So at this point, I do need you to go ahead and open up your 4G assignment and give me a green check. I do need green checks from 100% of you. Green checks once you have your assignment open and you've clicked Start Quiz. I'm going to give you 45 seconds to do that. If it's just being slow, you can still give me a green check if you have at least clicked on the link. Green checks once you have opened your assignment or once it's loading. Waiting on some green checks. If I don't get your green check, I'll go ahead and move you to the check-in room so you can regroup and come back with us. Nathan, Ronan, Ryan, W. Green checks, please. Nathan, Ronan, Ryan, W. Thank you, Nathan. Ronan, Ryan, W. Just waiting on your 2 green checks. Hello, Ronan, are you there? Ryan, are you there? Please give me your green check. Red X if you're having trouble opening the assignment. So please make sure I know that you're here. Awesome. I see Ronan typing. Okay, it's opening. Perfect. Thank you, Ronan, for letting me know. Ryan, you're the last person I haven't heard from. Please go ahead, type in the chat box or give me a green check. Let me know that you are ready to work with us. Ryan W. Ryan S, you're good. All right, awesome. Thank you. Ronan, just give me that green check once it's opened for me. Perfect. All right, everybody, so let's go ahead and do a quick brainstorm. So let's take a look here. We have a mixture of some water and sand. You can see here that we then pour it into a funnel that has some filter paper. And what I want you to notice is what is happening to this mixture. Go ahead, tell me in the chat box, what do you notice happening from start to end? What has changed about the mixture? In the chat box, let's get some more participation. Thank you, Annette. I see Sylvia type in the chat box. I see Annette typing. Yes, what do we notice happening? Make sure you tell me your observation, even if it's similar to someone else's. This still helps to reinforce your own learning. Remember, you're the only one in charge of your learning. See you in the chat box. Perfect, Annette. Yes, we can definitely see for sure that the sand and the water seem to be separating. Now, what I want you to notice, though, is that the sand seems to be on top of the filter paper. And why do you think the sand did not go through? Why do you think that the sand did not go through the filter paper to the bottom? Think about what you know about sand versus water. Why might sand not have made it through the filter? Chat box, I see Natalie typing. Yes, awesome, great answers. Yes, all of those would make sense to me, right? So sand is a solid, which also means that it is heavier, right? Meaning like it's denser, right? It is also thicker, absolutely. And so sand, therefore, probably can't make it through the holes of the filter, right? So can't make it through. So again, these things are being separated, but what I want you to notice is regardless of if they're mixed together or separated, are they chemically still water and still sand? Has their chemical identity changed at all? Has chemical identity changed at all, yes or no? Chemically, is the sand still sand? Is the water still water? Has their identity changed at all, yes or no? No, they're still completely identical. Okay, that's good to know, Ayla. Let me go ahead. I'll put that into my notes right now. Yeah, I think when you answered on the survey, it might just have been too ambiguous for us to know for sure. So no worries. Let me go ahead and get that in there. Perfect. Thank you. All right, looking good, everybody. So let's go ahead and talk about this. So this means that if they have the same chemical identity from start to end, this makes it a mixture. Remember, mixtures are when different types of matter are only physically combined or blended, meaning they are not chemically changing at all. So mixtures can be physically separated. They could be separated using filters, using evaporation. Evaporation is a physical process where water is still water, even if it's evaporated. Or they could be physically separated just by like you picking out pieces, right? So mixtures can be physically separated, meaning you don't need a chemical reaction. You can see some examples here too, right? If you have sulfur and iron mixed together, you can actually use a magnet to remove the iron. But again, the sulfur and iron is still chemically sulfur and iron, no matter if it is mixed together. In the chat box, give me a smiley face if that makes sense. Mixtures are only physically combined. They do not chemically change. Chemical identity is still the same. Great. All right, so let's go ahead and make sure we understand this. I'm going to go ahead and give you your tools on the whiteboard. Go ahead and box or check off which of these statements are correct about mixtures. Are mixtures physically blended? Are they made up of only a single type of matter? Must they be separated by a chemical reaction, or can they be physically separated like with a magnet? All right, go ahead and circle all of the correct statements or box all of the correct statements on the whiteboard for me based on what we just discussed about mixtures. Sylvia up there. Ryan, Annette working on the board. Great, keep on working up there. Get your participation up there. Thank you, working hard, everybody. Madison, Kyrie, get your answers up there. I haven't seen your participation on the board. Jennifer, you as well. Gabe, Gabby, Anthony T, go ahead and get your answers up there. Thank you, Ayla. I see you up there. Perfect. All right, let's go ahead and check this out. I'm going to go ahead, pause your tools, and I would definitely agree for sure, right? So mixtures are physically blended. That is definitely true. If you take a look down here at this example of a mixture, you can see that the oxygen is still oxygen and the hydrogen is still hydrogen. They are only physically blended together, which also means that they can be physically separated through evaporation, through a magnet, through a filter, through picking out the individual pieces, depending on how big the physical mixture is. All right, so all of these can be physically blended and physically separated. Great job. This is going to be number 1 in your assignment. Go ahead, give me a green check when you have this saved. You have 30 seconds. Make sure you check off both of the correct answers. Green checks for number 1. Make sure you read carefully. They may be scrambled, so make sure you read carefully. Nathan, green check, please. Ryan S, green check. Gabby and Anthony T. Let me know if you need help. Otherwise, please give us green checks for number 1, letting me know you're ready to move on. Perfect. Thank you. Anthony T, Nathan, Ryan S. All right, I'm going to go ahead and move on. Thank you, Ryan S. Anthony T, Nathan, green checks, please. Thank you, Anthony T, Nathan. Hello, are you there, Nathan? Green checks for number 1. Nathan, green checks for number 1. All right, so again, we just talked about this. Mixtures happen when matter is physically blended or combined. And now we're going to go ahead and talk about what are the different types of mixtures. So the first type is they can be homogeneously blended. Again, this is actually a term that we already know. Remind me, in the chat box, homo, this prefix, does it mean same or different? Does the prefix homo mean same or different? Go ahead, tell me in the chat box. This is all review from Unit 1. Yes, exactly, Sylvia. So homogeneous mixtures look the same throughout. We also call this a solution, which I told you that today's lesson is about solutions. So that is why this is important to review. They look the same throughout, and they're completely dissolved together so that there are no visible particles. So for example, when you mix salt with water and it's all mixed up, that salt water looks no different from regular water. You could accidentally drink it, and that would be the only way that you would notice that it is different, is because it would taste salty. But look-wise, it looks the same as just regular water. Heterogeneous mixtures, on the other hand, are blended non-uniformly, hetero meaning different, and so they do in fact look different throughout. So there are 2 visible components. That could be, for example, oil and water, or a mixture of gravel, or even paint. If you let paint settle for a long time, there's a thinner part that floats to the top and the thicker part goes to the bottom. Those are 2 different components that have to be mixed together before you can actually begin painting. All right, let's go ahead and take a look up here. So we want to identify which diagram is homogeneous and which diagram is heterogeneous. Go ahead, what we want to find for homogeneous is we want it to look the same throughout. So we want 2 samples to look the same. So let me go ahead and annotate this. So we want 2 samples to look the same, whereas heterogeneous, we want 2 samples to look different. So I'm going to go ahead and take 2 samples from each of these, and I want you to identify, do those samples look the same to each other or different, and that should help you identify if it's homogeneous or heterogeneous. All right, so here's the first sample for this one on the left, and over here is our sample over here. All right, so go ahead and on the whiteboard, go ahead and write, do you think this one on the left is homogeneous or heterogeneous? Do the samples look the same? That's homogeneous, or different? That's heterogeneous. And then same thing on the right. Is this homogeneous or heterogeneous? Take a look at the 2 samples. Do they look the same or different? Remember, if they look the same, that's homogeneous. If they look different, that's heterogeneous. Go ahead, get your answers up on the whiteboard. You don't have to worry about spelling. Spelling's already there for you, so just copy those words up for me. So again, homogeneous means that the 2 samples look the same. So we have a sample up here, a sample down here. Do those samples look the same? That would be homogeneous. If those samples look different, that would be heterogeneous. Compare the 2 samples. Does the top sample look the same or different as the bottom sample? Same thing over here. Does the top sample look the same or different as the bottom sample? Awesome, there we go. Fixing some of our mistakes there. pause those tools. So yes, this one on the left is definitely going to actually be heterogeneous, right? We have a completely pink sample on top and a completely green sample on the bottom, which means that we have two totally different samples making this a heterogeneous mixture. Go ahead in the chat box, give me a star if that makes sense. This one on the left is actually heterogeneous because if I were to zoom out, I would see part of the mixture being pink and part of the mixture being green. It would look very different. Excellent. Now on the one on the right, both of these two samples actually look the same. Each sample has two greens, two pinks. They are all evenly distributed, and so this one would actually be homogeneous. Excellent job. All right, so again, heterogeneous, a sample from the top versus a sample from the bottom look different. Homogeneous, all of these samples look the same. They all have the same components, the same amount of each part. All right, so we've talked about homogeneous, they're blended uniformly. They can also be called solutions, whereas heterogeneous mixtures look different throughout. Again, still only physically combined. There is no chemical reaction happening. Go ahead and match these up for me on the whiteboard. You have your whiteboard tools. Please use thin lines, any color but red, and match these up. We have mixtures, heterogeneous, homogeneous. Which one is the one that's blended uniformly, also called the solution? What is it called when different types of matter are physically combined? And which one looks different with two or more visible components? Again, take a look at those prefixes. That will help you figure out which is which. Go ahead, get your answers up on the board. Beautiful. Let's go ahead and pause those tools. I like all those colors. Blue in particular is very pretty. All right, so let's go ahead and take a look at this. I'm going to go ahead and grab my red tool. So yes, a mixture is going to be when different types of matter are just physically combined, meaning they can also be physically separated. Heterogeneous, remember that prefix hetero does in fact mean different, so they look different throughout. Whereas homogeneous means that they are blended uniformly and look the same throughout. And remember, a synonym is also called a solution. Excellent job. This is number 2. Go ahead and give me a green check when you have this saved. I'm going to go ahead and send those to you, the link in the chat box again. Green checks for number 2. Match those up. You have 45 seconds. Here we go.
100% green checks. Great job, everybody. Okay, so now we're going to go ahead and break this down even further. So heterogeneous mixtures actually come in 2 different types. The first is that they can be called a suspension, which means it's a mixture of physical particles that appear uniform but eventually settle out. Much like our paint, for example, we talked about how the paint, you have to shake the can up after it's been sitting for a long time. So suspensions, again, they have particles that do appear uniform for a little bit, much like a solution or a homogeneous mixture, but they do eventually settle out. They are only temporarily suspended. So you might often hear the term like must be shaken well. How many of you have ever seen that on like a carton in your refrigerator? Go ahead, give me a thumbs up if you've ever seen that on some food item in your refrigerator, like orange juice, for example. Or yeah, so shaken well, that is a suspension. Other examples might be like cough syrup. Cough syrup sometimes says that it needs to be shaken well. That way you can see the particles are suspended throughout the like gel that it comes in. And flour and water would also be an example of a suspension. Okay, and I can go ahead and show that to you. So if you see here, right, so this right here is flour and water, and you can see that it has definitely settled out. And if I were to stir it up, for a little bit, it would look uniform and like a solution. But eventually, if I just keep on letting this wait, eventually it will settle back out to what you originally saw, where all the flour kind of sinks to the bottom. So that's a temporary suspension. Okay? A colloid, on the other hand, is a uniform mixture of particles that are permanently suspended, which I know is a little bit confusing because it would make more sense to call this one a suspension. But just think about a colloid, they are not going to settle. Okay, so suspension, they settle. Right, so that's how I remember it. Instead of thinking about the word suspension, I just think of settling. So suspensions settle, whereas colloids do not. They do not physically settle out, but you can still tell that there are particles in the mixture. So examples would be whipped cream, fog, smoke, processed milk, and mayonnaise. These are all kind of cloudy mixtures. So they're not going to be complete solutions because solutions dissolve to where you can see through them. These things are not dissolving enough to be able to see through them. Go ahead, give me a car in the chat box if this makes sense. So in colloids, they're getting closer to solutions, but not completely because you can still see evidence of the particles. Now, there's actually proof of this, all right? So if we take a look here, I have some milk. Okay, and milk is an example of a colloid. And if you were to shine a flashlight through milk, all right, what you can actually see is milk actually glows, which is pretty awesome to look at. All right, so milk will actually glow because the light is bouncing off of the particles. So the particles are not tiny enough to completely dissolve, and so they're still a little bit big, and so that light actually bounces off and makes the milk glow, which is awesome, right? If you were to take a look at a solution instead, so for example, I have salt in water. Let me go ahead and mix it up and dissolve it. All right, so this is going to be salt in water. Okay, so salt will completely dissolve in water. It still looks like water, right? And this time, the light is going to go completely through. So it's a little bit harder to see right here, but the light is actually going completely through. It's not making it glow, besides the fact that you can see the light. All right, smiley faces if that makes sense. All right, so again, milk, it disperses it completely. So you can see lots of glowing, whereas water, it allows the light to just travel through. All right, so water allows the light to travel through. Awesome, everybody. All right, so that is the difference between suspensions and colloids. So again, we've talked now about solutions or a homogeneous mixture. Those ones have really tiny particles. The particles are so tiny that they're transparent and you can see through them. The particles totally dissolve, like in salt water, and so that is like salt water or sugar and water. You cannot see any evidence of the particles. Heterogeneous mixtures can be split between two groups. Colloids are kind of in the middle. Colloidal solution is cloudy. You can't really see through it. It glows due to light bouncing off the bigger particles, but it is permanently suspended. So the particles aren't so big that they fall. They are permanently suspended, again, like milk, fog, or smoke. Suspensions, lastly, are the ones that actually do settle out. So their visible particles are only temporarily suspended. Their particles are much bigger, so they begin to fall. This is like cough syrup, flour, water, things that you need to mix well. You need to be able to match these up on the next slide. Go ahead and give me a lightning bolt if you feel like you're confident to do that. Broken heart if you are confused about any of these definitions. Lightning bolt if you feel pretty confident. Broken heart if you're confused. Awesome. All right, let's go ahead and try it out. Oh, sorry, I guess it must be on the next slide. All right, so again, here's our overall mind map. Mixtures when matter is physically blended or combined. Homogeneous ones are blended uniformly and are called solutions with really tiny particles that are transparent. Colloids have medium particles. Those are heterogeneous. They look different throughout. They look cloudy. Their particles are permanently suspended. They do not settle out, but they are still big enough for us to notice. Suspensions, on the other hand, have really large particles, and so they do settle. Think suspension, think settle. All right, let's go ahead and match those up on the whiteboard. You have whiteboard tools, go ahead and do those. So solution, colloid, suspension, heterogeneous mixture of permanently suspended medium-sized particles like fog, homogeneous mixture that looks the same throughout of small-sized particles like salt water, and a heterogeneous mixture of large-sized particles that settle out, flour and water. Think about that word settle. Which one does that remind us of? Excellent. I see Amy, I see Annette, Sylvia on the board, Ayla on the board, Ryan S. Let's get some more participation from Ronan. Want to see your lines up there. Nathan, Natalie, I see you up there. Thank you, Ronan. I see you up there. Madison, Kyrie, get your participation up there. Madison, Kyrie, thank you. I see Ken on there. Kevin, want to see yours. Anthony B, Anthony T, go ahead, get your participation up there. Thank you, Kevin. Jose, Jennifer, Gabe, Gabby, go ahead and get your answers up on the board. Looking good. Thank you, Kevin. Thank you, Kyrie. Awesome job, everybody. Love it. All right, let me go ahead and pause those tools, and let's take a look at this. Perfect. So yes, solutions, again, solutions are a synonym for homogeneous. Those ones are so tiny that their particles completely dissolve, like in salt water. Colloids are permanently suspended medium-sized particles, again, like milk or fog. Suspensions are only temporarily suspended, which means their particles do settle out, whereas colloids and suspensions are both heterogeneous. They look different throughout. Great job, everyone. This is number 3. Again, colloids think cloudy, suspensions think settle. I'm going to go ahead and give you 30 seconds. Please answer number 3. Green checks for number 3. Go, go, go. Looking good, everybody. All right, let's go ahead and move on. So now we're going to go ahead and zoom into talking about solutions. Again, this might seem like a weird change from talking all about chemical equations and balancing and doing calculations, but this will make more sense tomorrow because tomorrow we are going to talk about molarity, which has to do with moles and solutions. So that's why we're reviewing about solutions right now. So again, solutions have really small particles. They are homogeneous mixtures, and they are made up of 2 new words that we're going to learn today. So they are a mixture of a solute and a solvent going into a single phase, meaning it becomes all liquid or all gas, or it becomes all solid. So an example of a solid solution would be brass, which is made up of copper and zinc blended uniformly together. An example of a liquid one would be soda, which is sugar, water, and carbon dioxide gas all blended together into a liquid. And an example of a gas would be air. Air is made up of mostly nitrogen and a little bit of oxygen that is mixed together into a single uniform solution. Awesome job, Ronan. All right, so here's what we're going to take a look at. So solute and solvent are the 2 parts of a solution. So you can see that right here. Solute plus solvent makes a solution. Now, solute is the substance of whatever there's less of. All right, so it's what we have the smallest amount of. Essentially, it's what's getting dissolved. The solvent, on the other hand, is what is we have more of, the larger amount, and this is what is actually doing the dissolving. So for example, you'll often hear in our class and in other classes that water is the universal solvent. Universal meaning that it can dissolve the most things. So water can dissolve the most things, the most substances. Now, it can't actually dissolve everything. So, for example, water cannot dissolve oil, but compared to other possible solvents, water is the best of them. All right, go ahead and give me a lightning bolt in the chat box if that makes sense. Water is the best of the solvents. Universal not meaning that it can dissolve everything, but that it can dissolve the most things. Excellent. All right, so let's go ahead and take a look at an example here. All right, so if I have, here we go. Sorry, where'd my spoon go? All right, if I have some water right here, and I'm going to go ahead and get some powdered drink right here. This is Tang, my husband's favorite drink. All right, so here we go. What do I have less of? Do I have less of the powder or less of the water? Go ahead, tell me in the chat box. What do I have less of? Yes, I see Annette. I see Ayla typing. I see Ronan. Yeah, we have less of the powder. Thank you, Amy. So if we have less of this, is the powder the solute or the solvent? Based on what we just defined, if this is what I have less of, is this the solute or the solvent? Let's get used to using our vocabulary. Yes, this is going to be our solute. Now the water, that's what I have more of, and water is the universal what? Again, this is what's doing the dissolving, therefore it is called the what? Sorry, I'll turn off the video for a moment because it's lagging for most people. Water is the universal what? Yeah, this one is going to be the solvent because it's what's doing the dissolving. And then when I finally put them together and mix them up into a uniform mixture, what is that uniform mixture called? Go ahead, tell me in the chat box. That uniform mixture is called a what? Yes, exactly. I see Ronan in the chat box. What is this called when they finally get mixed together? Yes, they are called a solution. Awesome. All right, this is going to be number 4. So go ahead, give me a green check when you have number 4 saved. Fill in the blank with the word universal. You have 30 seconds to do that. Make sure you spell it correctly. It's kind of a longer word, so focus on your spelling. Go, go, go. All right, waiting on green checks from Ken, from Kyrie, Madison, Nathan, Ronan. Green checks. Ken. All right, green checks, Ayla, Ken, and Nathan. Don't want to leave anyone behind. Green checks for number 4. Anthony, Ken, Nathan, Anthony, Ken, Nathan. All right, cool. Let's go ahead and talk about this. All right, so there's an easy way to remember which of these is which. All right, so what I want you to notice is please in the chat box count up for me how many letters do you see in the word solute? How many letters do you see in the word solute? Yeah, exactly. It has 6 letters. All right. How many letters do you see in the word solvent? How many letters do you see in the word solvent? Yep, count them up. Yep, there are 7 letters. And lastly, how many letters do you see in the word solution? Perfect. Yeah, so this is going to be 8 letters. So this is how you can actually remember this because the shortest word is what you have less of. So this is the shortest word, and this is actually whatever substance you have less of. So substance that you have less of that is getting dissolved. Getting dissolved. All right. And then 7 letters, the solvent is going to be the medium word, And so this is the substance that you have more of, and what's doing the dissolving. And then finally, solution is the longest word. And so that means that this is going to be both the solute and solvent mixed together. So this is the overall final solution of everything being mixed together. Sorry, I should say final mixture, because we don't want to define the word with the word. All right, so that's an easy trick to help you remember which of these is which, and we will make sure to apply that tomorrow when we also talk about molarity. Go ahead and give me a star if that makes a little bit more sense. This is an easy way to remember because I do know they all look very similar. So solute, think it's the shortest word, it's what I have less of. Solvent is a longer word, it's what I have more of. And solution is the longest word, the final overall mixture. Great job, everybody. All right, so make sure you submit the assignment. Go ahead, tell me in the chat box, how did we do today? Tell me in the chat box, how did we do today? Awesome, awesome. All right, if you didn't do as well as you wanted to, remember that the recording will be uploaded around 1 to 2 p.m. and you can always try again. You always get 3 attempts, so check out whichever question you got incorrect and just try it again next time. All right? So we talked about mixtures and solutions today, homogeneous versus heterogeneous mixtures, and we learned some new definitions: solution, solute, solvent, colloid, and suspension. How are we feeling about that? Go ahead and show me up on the whiteboard. How are you feeling about today's objectives that we went over? Looking good. I see Amy up there, Christine, Jennifer, Kevin up there. I can't tell who's who, so don't worry about that, but don't be shy. Awesome. I see Annette. Looking good. All right, so again, if you don't feel super confident, remember that you can always watch the recording again, or you can always email me, and I'm happy to set up an individual tutoring time as well to help you out individually. So that is definitely an option as well. Thank you. I see Kyrie up there. Perfect. All right, everybody. So for today's attendance, I'm going to go ahead and grab the link to it. So today's attendance, what is the substance that gets dissolved that we have less of called? Go ahead, tell me in the chat box. Is it the solvent, solute, or the solution? What do we have less of? Remember our trick that we just went over, count up the letters. Which one do we have less of? Perfect, yes. So please make sure you actually write your answer in a complete sentence. So the correct answer is the solute is what we have less of. All right, so that is the actual answer for today. The solute is what we have less of. Please make sure that that is what you actually write. So let me go ahead and, there we go. Star it. All right, so what's in the star? That's what today's attendance is. All right, link is in the chat box. Thank you so much, everybody, and I hope you have a wonderful day. Let me know if you have any questions, but otherwise you are dismissed, and I will see you bright and early tomorrow. More like midday tomorrow. Bye, everybody. Have a great day.